In this video, we're going to introduce ourselves to organic synthesis. You're going to use organic synthesis on your next organic chemistry exam and every exam until you're finished with all of organic chemistry. So this is an important video. We're going to look at nucleophilic substitution as a method of synthesis. To do so implies that we need to make a nucleophile. Acetylene can be made into a nucleophile. Reminder, acetylene is also called ethyne. To make acetylide, which is our desired nucleophile, we have to keep in mind that acetylide is the conjugate base of acetylene, so this is an acid-base problem. The pKa of acetylene, as is the pKa of all terminal alkynes, is 25. For this equilibrium to go almost exclusively to the right, we need a number here for this acid. I know it says H base, but you know that's the conjugate acid of this base. I need the pKa of that acid to be greater than, you guessed it, 25. We have some candidates of bases that can do this. But before we do that, we have to remind ourselves that the conjugate acids of these bases, these are the ones I picked because they all have a pKa above 25. So these are the acids. This is not the answer to my question. The conjugate bases are going to be the answers to my question. And the conjugate base of ethyne, which is the first one right here, and the conjugate base of ethyne, and the conjugate base of ammonia, or an amine, or the conjugate base of H2 are going to be in this box. They all have a spectator ion listed first, and the anion, ethyl minus, vinyl minus, NH2 minus, and H minus, also known as hydride. These are the bases you can use to make acetylide. If you attempt to use these bases, you will not get any credit. Sodium hydroxide is kind of crossed off there. Let's take that, make it a little clearer. Sodium hydroxide is not a good candidate. It's the conjugate base of water, and water has a pKa of 16. Another example that would fail, potassium carbonate is the conjugate base of bicarbonate with a pKa of 11. If you attempted to use either one of these bases here, you wouldn't get any acetylide at all. So, with this knowledge that we have of methods of making acetylide, let's learn a new reaction that can make a carbon-carbon bond. And you might not know this yet, but making carbon-carbon bonds, that's what we call synthesis. Specifically, organic synthesis. The new question is, what molecule can I react acetylide with to make this new carbon-carbon bond to a butyl group? Well, I hope you understand that we need some kind of butyl group. For the anion to be attracted to the carbon on the end needs to be at least slightly positive. So we need to have some kind of butyl group with a slightly positive carbon. Butane does not fit the bill. Butane's not positive at all. To make carbon slightly positive, we attach them to electronegative atoms, such as chlorine. The combination of chlorine being electronegative, which makes the carbon feel slightly positive, and the fact that chloride is a stable species makes this an ideal candidate, as opposed to this molecule, an OH. This molecule has no interest in liberating OH. OH minus is not stable. So this does not work because this is not stable. And we call that a situation where a species that wants to leave won't leave because it's not stable. We say that it is not a good leaving group. Good short form for leaving group would be LG. Chloride, on the other hand, is a very good LG. And you're asking yourself, how do I know what the good leaving groups are? The answer to that is pretty simple. This is not an exhaustive list of molecules that will work here, but it's pretty good. If you look, the leaving group here is chloride, bromide, iodide, and toluene sulfonate. Looking back to chapter 4, these are all the conjugate bases of what kind of acids? HCl would be the acid, HBr would be the acid, HI would be the acid, and HOTS. Those are strong acids. I will fix this in a second. Good leaving groups are the conjugate bases of strong acids. So let's look at the actual mechanism for this reaction. It's a very simple mechanism, the simplest of the semester. Here we have acetylide, the nucleophile. We have 1-chlorobutane, the electrophile. The lone pair on the acetylide is attracted to the carbon with the halogen because that makes the carbon quite positive. And that kicks off the stable leaving group. So we made a bond from acetylide's anionic carbon to carbon 1 of butane. That's synthesis. Acetylide was the nucleophile. There are 2 molecules here. That is a little large. So reading this backwards, we have bimolecular when 2 molecules come together. One of them is a nucleophile, this one right here. And the acetylide that ends up in the new molecule has substituted for the chloride. There's your S. Bimolecular nucleophilic substitution. Here is your introduction to organic synthesis. I hope this video has been useful, and I look forward to our next one.